Assalamu alaikum wa rahmatullahi wa barakatuh. Lecture 18 is going to be a tutorial where you're going to solve a couple of problems and I'm going to give you some hints and information. Okay, problem 3-15. The gas phase reaction, half moles of nitrogen plus 1.5 moles of hydrogen give you ammonia. Is to be carried out isothermally. The molar feed is 50% hydrogen and 50% nitrogen at a pressure of 16.4 atmosphere and 227 degrees C. Okay, what's required here is to construct a complete stoichiometric table. We learned how to construct a stoichiometric table, and we want to also calculate CI naught, which is for nitrogen, hydrogen, and ammonia, but not on the feed, and delta, and also epsilon. Okay, obviously, if you want to calculate delta and epsilon, you'll need to rewrite the above equation in such a way that you'll have a stoichiometric number of 1 in front of the limiting reactant. So you need to rewrite the stoichiometric equation again in such a way you have 1 either in front of N2 or 1 in front of H2. So you decide first, you find out which one is the limiting reactant. Okay? Okay. Then you need to calculate the concentration of ammonia when the conversion of hydrogen is 60% if the reaction was carried out in a plug flow reactor. And part C, suppose by any chance the reaction is elementary with Kn2 equals 40 liter per mole per second. Write the rate of reaction minus RH2 solely as a function of conversion for the system and that system. Okay, so you need to write minus RH2. That means if you not write minus RH2, this means you need to use K, right? K H2. You need to use K H2. Okay, however, you have only here K N2. So you know how to convert Kn2 to KH2. That's one thing. The other thing is that you should actually think how to write the rate law. Of course, the rate law here says suppose that reaction is elementary. So that means the rate law that you're gonna write is based on the equation as given with this stoichiometry. I know that you have rewritten this to have, for example, 1 in front of H2, right? However, you're not going to use that new stoichiometry. You're going to use this stoichiometry because the question is referring to this reaction written with these stoichiometric coefficients. Okay, guys? So please be careful there. Okay, we have another problem here. Let's read it together. It is necessary to produce 30 pound-mole per day of C from A and B in a constant volume batch reactor. The volume of the batch reactor is given. The reaction mechanism is as follows. A plus B gives you C plus D. The value of K is given as well, where CA naught equals CB naught. The value is given. The question is, for how long the reaction should be allowed to carry out? For how long the reaction should be allowed to carry out. So we're talking about T reaction per batch. So seems like we're gonna repeat this process in different batches, in different cycles, because one batch will not be enough to meet this production requirement. So per day we need to run more than one batch, more than one cycle. So again, for how long the reaction should be allowed to carry out per batch to achieve the desired production rate, if the downtime is 0.2 hour per batch. So remember, we have time for preparing the reactor, and there is time for the reaction TR, and then there is time after the reaction to prepare it, to remove all the products and reactants from the reactor, and then to clean it up, prepare it for the next batch. So all of these times required, which are not part of the TR, is called or titled as downtime. Okay, so how are we gonna find the required reaction time per batch? Good question. In order to answer this question, let's ask ourselves a few questions. First, can I produce the desired amount, which is 30 pound-mole per day, in one batch? And of course, this huge number cannot be produced in one batch. How do you know? Well, look at the maximum number of moles that you can produce per batch. So in one batch, you have, this is C naught, and this is V. So if you achieve 100% conversion, then how many moles of C you will get? Obviously, you would calculate how many moles of A you're initially putting. So Ca naught times V gives you actually the number of moles that you are initially putting into the reactor. And if you have 100% conversion, that would be the amount of C that you'll get. And it will be much lower than 30 pound-mole per day. So obviously, I cannot produce this amount in one batch. Then the second question, shall I allow for high conversion in each batch? So should I leave the reaction to proceed until I get high conversion? Well, of course, in question 1, we decided that one batch will not be enough. We have to repeat the batches, like carry out the process or the reaction for more than one batch. But the question here is, should I allow each batch to extend for a long time in order to achieve high conversion? Well, if I do this, I reduce the number of batches per day, correct? Okay, let's see what question 3 is about. Shall I operate with high number of batches per day? Should I run high number of batches per day, for example, 30 batches per day? Okay, if you run many batches per day, that's fine. You'll be able to produce some good amount of C in each batch. But the problem is, this amount of C that you produce is not a lot. Why is that? Because if you increase the number of batches per day, that means that every batch would take less time, correct? And less time allowed or allocated for each batch means low conversion in each batch. So you're not going to produce much C in each batch. So then how can we solve this problem? Well, we're gonna develop together our one-dimensional equation. See? So let's see. NC per day. So how many moles of C producing per day? Has a unit of pound-mole C produced per day. How can we calculate this? By unit conversions, right? Let's look. NC, which is the pound-mole of C produced per batch per reactor, right? NC is number of moles of C produced per batch in every cycle per reactor. We multiply it by number of batches per day. Batches per day. How many batches are you going to run per day? Only one batch? Obviously, one batch will not be enough to produce this much amount. Okay, and multiply by number of reactors. So sometimes we need to use more than one reactor, especially if the volume was small. Okay, so of course in this example we have only one batch because it says a constant volume batch reactor. So however, we need this variable in order to fix the units. So let's see, number of reactors cancel out with reactors, number of batches cancel out with number of batches, and what is remaining is simply pound-mole C produced per day, because I have cancelled out batches with batches and canceled out reactors with reactors. So now the units are consistent on both sides. Okay, so can you do that? Obviously you can do that because you can use stoichiometry to find an equation for this NC. Okay, so you know how to find NC as a function of conversion, right? And let's see, how do you calculate number of batches per day? How do you calculate number of batches per day? You know how to do that? Okay, so let's learn how to calculate the number of batches per day. It's a very simple equation. Again, depends on the unit conversion. So we want number of batches per day. Okay, so it's simply, let's see how many hours we have per day. We have 24 hours per day. We divide it by the time required for every batch, for every cycle, I mean, and that is hour per batch. And if you cancel the units, you'll get batches per day. So for instance, if every batch takes 12 hours, so that would be 24 divided by 12, that is 2 batches, correct? You can run 2 batches per day. Okay, so let's see the time required for every batch, or the time for every cycle, or the total time for every batch equals the downtime, right? The downtime plus the reaction time, correct? Okay, the downtime, we have it already specified, 0.2 hours. And let's see where we get the reaction time from. Any idea where how can we calculate the reaction time? Yes, we can calculate the reaction time from the design equation, right? Batch reactor design equation. And obviously we can find it as a function of X. Therefore, the number of number of moles of C produced per day equals, in this case, the number of C produced in each batch, which is function of X, correct? Higher X means more C you can produce per batch, times the number of batches per day, which is function of X. We just found that this equation is function of X because TR is function of X, times 1, which is the number of reactors that we have. Therefore, now we have only one unknown in this equation because the NC per day is given, and here we wrote this equation as a function of X, correct? NC we found it as a function of X, so we can find it as a function of X, and B is a function of X. The only unknown is X. We can find X from this equation and then plug it back into TR, and we can calculate the number of batches per day and so on. Okay, so there we go. The answer is 1.2 hours because once we find X, we can plug it into this equation. Here we go, and we can find TR, which is the reaction time per batch. What I did here is I used this equation and I plotted NC, the production of C per day, as a function of X. Here we go. This is X, and then I calculated NC pound-mole per day, but also I plotted the number of batches per day as well, this guy, and also plotted TR, which is this guy. So, and you can reflect upon this figure and learn a lot from it. Okay, with this we reach the end of today's lecture. Thank you very much and enjoy working in those two example problems. Bye for now.